All right, welcome back, and we are going to continue talking about sensory systems. So today we're talking about hearing, which is another one of your mechanosensory systems, because in hearing, what you're doing is literally responding to the physical waves that are formed from sound. You're taking those waves in and translating them into information that is useful. So the underlying anatomy for hearing, I think, is kind of one of the coolest, they're most beautiful looking structures. But it is a little bit complicated. I don't want to overly complicate the whole thing. But the main idea is, if we look here, and we're sort of looking at cross-section, right? This is your ear, right? And this is your outer ear, right? That's the part you can actually see, connected to your eardrum, right? So hopefully we all are sort of familiar with that, right? The eardrum is this flap of skin, basically, or a membrane, that keeps then a bunch of fluid filled in. So on this side there's fluid, and on this side there's no fluid. And so when sound hits this drum, much like a Lego drum, it causes it to vibrate. And then it causes three other bones to move: the hammer, the anvil, and the stirrups. These are the three smallest bones in your body. And I can't honestly say I've ever had a good reason why we had to have all of this here, but for whatever reason, this is a system that works, and they vibrate this, and it translates that vibration into this next area here, where through the round window of the cochlea, it puts this vibration into another fluid-filled area. And this cochlea, this is the part that looks super cool, and you can find really cool microscopy images of this. I'm a little bit biased. I didn't work on the cochlea myself, but I worked in a lab that spent a long time, and I thought we had some of the sort of prettiest images that ever came out of that. So the interesting thing here, actually, though, is that you're vibrating this fluid here, and then in this sort of snail shell-shaped area here, that's the cochlea itself, there are, along all of this, sensors that respond to vibration. Because how this is all made up, and don't worry too much about the physics of it, at certain areas of it, you get lower frequency at the base, and then higher frequencies at the apex, right? So if there's a sensor right here at the tip, that's for your highest frequency that you can hear. And the sensors closer to here are going to be some of the lowest frequencies that you can hear, right? And based on all of this, there's really only, I think, somewhere in the neighborhood of sort of about 8,000 different sensors here. And these sensors are called hair cells. We'll get to that in a second, that can activate. So that's really all you can hear. And when this is also, I should say, the real reason why I think this is a sense we need to be extra protective of. We really worry about our vision a lot, but we have way more photoreceptors than we have hearing sensors. And these are very easy to lose. And we do lose it. We lose them sort of naturally over time. If you notice, for example, you may start to notice, but you can do this over time, you particularly start to lose the high frequencies throughout your life, and this is natural. It's not something to be worried about as long as you're doing it at sort of a normal pace, right? But I think we maybe even talked about this before in class, but we can actually use this sort of functionally where if you put out a very high frequency sound, some people will use that as a way to sort of keep away riffraff teenagers who they're still able to hear it, but the rest of the population is not. So it's really annoying to them, and nobody else hears it. Right. Right. So, anyways, each one of these sensors here then transfers their information when they're active to the auditory nerve that's going to go eventually to the auditory cortex. All right. So let's look at. Well, here, so if we look down here, you can start to see this is looking at how this is lined up. And if we look at these hair cells here, so that's what it's trying to show. So if we look and sort of take a slice down this way, and now look there, we have, this whole area would be the fluid that is being vibrated, right? And that vibrating is going to cause this tectoral membrane to move. And then right here, you have these hair cells, right? And they're called hair cells because they have these little projections that look very much like hair that sort of connect up against this. And as these move, they open these little channels. We've talked about these previously. They've got these tip links that open channels that cause action potentials to occur. and then that goes into the auditory nerve. I'm going to point this out because every drawing should show something that I don't think is terribly well explained. You actually have two sets of hair cells. You have these inner hair cells shown here, and then there's 3 rows of outer hair cells. And you'll see this quite often talked about as these being important. These hair cells, we actually don't even know what they do, but we do know, I shouldn't say that. We have some good guesses as to what they do, but we don't know with certainty. But we know they're not actually the ones that seem to be important for hearing. The real ones for hearing are just these inner hair cells, which again is a bit of a shame that we only have one and we have, sort of these in triplicate. What these seem to do, at least the one important thing that I've heard multiple times, is sort of readjust to sound. So basically, it's a way of thinking about gain, but we're probably familiar with this concept. If you've been in a loud room for a long time and then you walk out in sort of a quiet hallway and all of a sudden you can't really hear very well, and it takes, depending on how long you've been in that loud room, it might take a few seconds to a few minutes to even a few hours. What that is that these cells seem to sort of lock this in place a little bit. If it's super loud, they sort of clamp down, so it can't move quite as much. And if it's super quiet, they're going to relax more, so that this can move more and cause a reaction to this inner hair cell. And the reason is they're really protecting it. What happens, if we have sound-induced hearing loss, right? This is something familiar. If you go to a lot of concerts or from airplane noise, we know, or you should be well aware at least of the fact that that's going to cause hearing loss if you do that too much. What literally seems to happen for most of the time is these hairs, right? These tips on there and their tip links just kind of get sheared. They break up. So basically too much vibration breaks these up, and these cells can't regrow these, especially in adults. And so once they're gone, they're gone. So by sort of clamping down, that protects it from vibrating this too much to sort of destroy the cell. Right? So again, you go, sound waves come in through the air, they hit the eardrum. Now we're in sort of fluid area, right? Bounces around those 3 bones into the cochlea, which is fluid filled as well. And then through this snail shell, we're going to bounce that fluid around, and higher frequencies at the apex, lower frequencies at the base are going to be active, send their signals down the auditory nerve, right? So, and now I see where I just realized that I messed up. So I don't really want to record this. I'm just going to say this up. I was saying that the opposite just now, I'm pretty sure. And it's because I always get this confused. You would think base of the cochlea would mean lower sounds, but base actually meant higher sounds. And apex meant lower sounds. So just flip those around. This figure is correct, right? So as you get more towards the center of that curling up, you're going to respond to lower frequencies as opposed to the higher frequencies that are right there. And there's a YouTube video regarding that as well. So where do these project to? I said that auditory nerve, yeah, that's one of the cranial nerves, if you remember that, is going to project straight into your primary auditory cortex, which we talked about with music a little bit, right? So in this region, the key thing to note here is it's arranged by tone. So now I'm worried. I got to get this right. So the higher notes are back here, and the lower notes are down here. The higher tones are lower tones here, higher tones here, and that's corresponding to the apex and the base of the cochlea, right? And this arrangement here, which should start to see this repetition here, right, where the brain sort of repeats things over again. And we'll see something actually very similar for vision and how this is. But this whole arrangement is called tonotopy, right? So topography, like land topography, and tone, that should be obvious, right? So it's the topography of the brain is laid out by tone, right? So apex to base of the cochlea, low to high, right? Right. So that's the primary auditory cortex, where it's just receiving signals from the auditory nerve. Around this, right, is what we call the secondary auditory cortex. This is another sort of key principle of how the brain is arranged. We've gone through this again, talked about this with other things. So primary cortex is just simple tone-to-top, high pitch, low pitch. This area around it, the sort of secondary cortex, starts to break that down a little bit. This is where, things like when we were talking about music, how there was that region that seems to respond specific to music, that seems to be generally in the secondary auditory cortex. Similarly, there's regions that respond to specific aspects of voice and other sorts of noises, right? So this is a little bit more complex, a little stimuli it's responding to, and it's really starting to process these signals in greater detail to give us sort of a higher understanding of what that sound means. Without, you might have tones here, but without this, the secondary auditory cortex, it's all just going to be noise. All right. This is a question we'll talk about in class next time. So the idea of columns or laminar organization repeats throughout the brain. Why do you think this sort of laminar or columnar organization is a good idea? All right. So I'm not going to play this video. It doesn't make much sense to me to play a video within a video, but I found this video to be particularly good at explaining the whole process as I had done previously works. They do make one error in here where they seem to show that the outer hair cells are the key cells, which hopefully again by now you realize they are not. So these slides, like all my slides, are up on Schoology for you to look at, and you can find that video here. Right, so where do these signals go? I mentioned that they do all go from the ear through the auditory nerve to the auditory cortex. And this is sort of showing a coronal view here, a frontal view here, right? So that's where it goes. And again, they're going to do mostly this sort of crossing over thing. But there's a few pit stops they make. And I don't want to dwell too much on this, but I want to get the bigger picture here. If there's one you should know, it's the inferior colliculus. That we've talked about this before. The superior colliculus will actually be for vision. The inferior colliculus is for hearing. And there are a lot of times we see that, especially vision and hearing sort of reuse the same brain circuits, or not reuse them, but they sort of duplicate them. They look very similar. But the key signal thing here is that sound is going to come in, and we're showing blue is here from the left ear, or red is from the left ear, blue is from the right ear. But they are going to end up both being on both sides. Now, why is that important? Because as we'll learn about in a second, it is very important to tell where sounds come from to compare the left versus right ear. And we have to do this as fast as possible because we're literally using our brain to measure sort of wavelengths, right? And if you think about that, wavelengths tend to be measured in very, very small measurements. So within the brainstem here, even before it gets to the auditory cortex, there's a lot that's happening to help you respond to sort of basic aspects of this, to help you decide if there's a loud noise, do I turn my head right to look at it or left at it? Because this needs to happen instantly. And this whole circuit here is actually considered the fastest circuit you have in the brain. This is the action potentials that are able to move the quickest, because that timing is so critical to understand. So how do we localize sound? Again, it depends on sort of comparing your left versus right ear. And there's really three mechanisms by which this works, and we'll talk about each of these in a second, but there's sound shadow, time of arrival, and phase difference. And we use different strategies based on the pitch, right? So humans localize low frequency sound by phase difference and high frequency sound by sort of loudness difference. Let's explain those in details. So, right. So what's a sound shadow? So this is the idea that if you can imagine, you have a sound coming in from your right, and it hits your right ear, right? But then it's also going to hit your left ear. But because basically, if you think about it, your head itself is pretty good at absorbing sound. That means that in order to go through your head, some of that energy is going to be taken up, and by the time it gets to your left ear, it actually will be quieter. So it can tell that the difference between the right and the left, even if it's sort of minusculely quieter, your brain will understand that and be able to tell the difference. Also, not only is that's the sound shadow, but speed. We know that there is a speed of sound, right? Like we've done this before, I'm sure, right? If you look at an airplane and your brain is telling you it hears the sound at one location behind the plane, whereas it can see the plane further ahead. Or if you've watched fireworks before, right? You see the explosion happen, and some amount of time later you hear the sound, right? So sound is slow enough, even though it's still quite fast, that your brain, with these super fast circuits and action potentials, can tell the difference between when the sound hits your right ear versus your left ear. And it uses that to tell, whichever ear it goes to first is the one that's the direction more of the sound is coming from. Phase difference is a little bit more complicated to explain. So I do a sort of half job and hopes that you just kind of get this enough, to be honest, right? But the main thing is sound is waves, right? That's what we're looking at here. Up and down, this is a sound wave, right? And so over time, you might be at the top of the wave or you might be at the bottom of the wave. And so if sound was coming from the front, right, and it should hit both ears at the same time, that sound should be what we would call in phase, right? It should be identical. However, if sound is not quite coming from the same direction, then they will be slightly out of phase. And how out of phase they are will tell you which direction they're coming from. That should be good enough for our purposes. Right, so this is what this is trying to show here, right? If this is a sound wave traveling through the head, you can see that as it hit this ear, it was at this point in the wave, and at this ear, it's really more at this point. And that subtle difference can be enough. Okay. So, all of this should sort of explain to you why hearing aids are sort of imperfect, right? Originally, all hearing aids did was amplify sound. But this did not provide a great experience for patients. Sure, it was better, right? They could hear things they couldn't hear before, but it didn't work like hearing actually works for us. And we'll talk more about this in class. What do you think is missing? But I would say a key thing is actually, if we go back to this, look at how quickly our brains are comparing left to right ears. It's happening all the way in the brainstem. If we just have basically something that's amplifying sound here and here, there are some things that are going to get missed there. All right. So this is the last slide, and it's one of my favorite things to always talk about because I think this is a cool set of experiments, and it also is something I don't think most people know about. So owls, we are pretty good at localizing sound that comes left to right because we have two ears, right? No, actually though, we're pretty bad at localizing sound, knowing if it's coming from the front versus if it's coming from the back, right? Because the sound's going to hit the ears at the same time. We can't take effect of the sound shadow principle. It really feels the same to us front to back. And if you really think about this, you probably have noticed this before in your life. Similarly, we can't actually tell very well if sound is coming from above us or below us. Because, again, we just have the two ears on each side. Owls have kind of figured out a way to improve upon this, though, right? So we look at an owl, their heads look very symmetrical. But if you actually look at the owl's skull, and hopefully you can see there, right? This is the beak lined up front. Their ears are one on each side like you'd expect, but one is opening upwards, right? And the other one is downwards. And so this allows them sort of an extra comparison, what's coming up versus what is coming down. And they use this to have very good 3D sound localization. So how do we know this? One of my favorite set of experiments is this one where they took essentially baby owls and they put little prism glasses on them to sort of shift their field of view. Here it says 34 degrees. They did a number of experiments. Shifting, basically, you should be seeing something, if you were looking straight, but the prisms will make it shifted about 34 degrees one way or the other. And they let them grow up with these, right? And so that kind of set their visual map off, right? They learn just fine, right? Just like we would adapt to this as well. When you're very young, your brain is very plastic, and so it just learns, what normally an owl would think is 34 degrees. Well, no, that's actually straight in front, and your brain just sort of does that. But the thing is that their ears are also making a 3D map of this. And now, And what's very cool about owls is they kind of sync up these maps of their eyes and their ears very, very perfectly, I guess. Maybe that's a little strong word. But so then, when they're adults, they take off these prism glasses, right? But remember that plastic period is really only happening when they're younger. So that visual map and that auditory 3D map are set, and they don't really change that much. So, but now, where they used to be lined up, they're off by 34 degrees. What they went on the show is that we think of owls as having, really good night vision. And they probably do have, they do have better night vision than us, but they actually don't use that much, right? You can imagine, whereas vision should naturally get worse if there's less light, hearing, it doesn't matter if it's night or day. So owls seem to actually use their hearing much more, and particularly at night. And what they would show is that these owls, if they would have a little mouse, running around in these owl habitats, they would miss by these sort of 34 degrees. And it wouldn't actually be this. They kind of learned the owl strategy here. The hearing is critical for both the initial localization of where is that mouse that I want to prey on, and then basically right up until they got, I want to say it's like 6 to 18 inches, right? So the owls would sort of swoop in, and they'd be right there, and then they would switch over to trying to use vision. But since their vision was off, they would miss that last bit of the attack, right? So by doing all this anyways, we learned about how owls sort of develop these 3D auditory maps of the world around them, and they use that as sort of their primary sense for a lot of times for hunting, and how those maps sync up with the sort of visual 3D maps that they have. Anyways, that's what I have to talk about for vision, and we will go over this a little bit more, for hearing, when we meet up in class next. All right.